Just 1 minute. Yes, it is started right now.
Okay, so then we can start now. Good afternoon, everyone, and welcome to this series of the seminar series. First, I'd like to thank Mead, Shankar, and Shouro to organize this weekly seminar series. And it is great that Professor Guruprasad Kaur has agreed to give a series of lecture on physics of distilling, secrecy, and entanglement. So here, people who are from India and particularly from Kolkata, all of them know Guruprasad Kaur. But since here lots of people are joining from different other parts, so let me give a brief introduction of Professor Guruprasad Kaur. So Professor Kaur in Kolkata, he started this research on quantum information and quantum foundation probably more than 30 years, and he is one of the pioneering in this field in India. And officially only I think 7-8 students he has reproduced, but unofficially a huge number of people have get motivated from his teaching, from his research, with the discussion with him, and I'm sure that will be this will be extremely helpful for all of us. So Guruda, so what kind of things you prefer? So you will first give a talk, then at the end you will take the question, or in between you will also take
in between. If there is question, no problem.
Okay, fine. So in between, if you have some question, you can raise your question or unmute yourself and ask the question. Okay, so Guruda, you can start.
Yeah. Thanks, Manik, for the introduction, and also thank Mead, Shankar, and Shouro for running this seminar circuit. Actually, because of some other involvement, I could not attend most of these talks, but it is a very good initiative. And actually, I have decided to discuss the physics of distilling, secrecy, and entanglement, starting from Shannon. But today's talk is a little bit different. But somehow, when I spoke in S01 National Center, where Manik invited me to discuss, there I started with some results involving distilling secrecy from bound entanglement. So somehow I thought that it is important, but it is actually out of the circle of my actual program. But today, anyway, we will be discussing this part. But from next lecture onwards, we will be discussing starting from Shannon's theory. Okay, let me start. So we all know that if you have a bare state between Alice and Bob, it is a pure entangled state, so it cannot be correlated with the rest of the world. So we know 1 bit of secrecy you can get because this state cannot be correlated with the rest of the world. And sometimes you call it a private bit. The question is the following. For distilling a p bit, is the maximally entangled state is necessary. So if you have this 5+, of course, you have a 1 bit of secrecy, but whether this kind of a state is necessary for having a secret bit. If you consider, if you restrict yourself for 2-qubit system, the answer is yes, that this kind of entanglement is necessary. But in general, the answer is no, and most possibly it was in the last slide, I will show some references. There we will see possibly in 2005, the question was answered by Hortegi and some other people that there are some more general state from which you can also get a p-bit. But to understand that approach, let me start from the key generation protocol provided by Bennett, Prasad, and Marvin. The protocol is something like this. I think all you know that if Alice and Bob share a Bell state, the base state can be written in two bases. It actually in infinite basis, but we are using two bases, 0 and plus. And protocol is something like this. Alice and Bob both measures one of these spin observable chosen randomly from sigma x, sigma z, and record their choices, measurement choices and results also. Then Alice and Bob publicly discuss their measurement choice and not the results, and rejects the cases where the choice do not match. That means when they don't choose the same measurements, they reject all those cases. With the rest, they generate the key by using the following encoding. For 0 plus, it is 0, and for 1 minus, it is 1. In this way, they can generate secret key. But question is how to test that they are actually given a base state. Actually, if you measure sigma x and both people measure sigma x and sigma z, and if the results are correlated, then you know there is only one solution. Along both z and both x, if the results are correlated, there is a paper by Horodeki. If results of measurements in two labs are correlated in two different directions, then the only solution is a base state. So actually what they can do, instead of doing this thing, what they can do, they have been given many copies of 5 plus state by some base state provider, and what they can do, they can measure sigma x and sigma z, even sigma s and sigma z, and check the result for sigma x and sigma z measurement, whether the results are correlated. If they are correlated, then rest of the states, they are sure that they are 5 plus, then they need not actually have to measure along both the direction. They can measure only in the z direction and can get the key, because now they have been assured that their shared state is 5 plus. So in this way, you can also think the Bennett-Prasad-Marmin protocol.
Sir,
In that case, you need not have this encoding 0 plus 0
sir,
and
can you
1.
hear me?
Yes.
Sir, I have one question here.
Yeah.
And the question is, so this protocol is actually somehow measurement device dependent, right? Alice and Bob.
I am within quantum mechanics.
Okay, good. Okay.
Surely. And I will remain in quantum mechanics.
Okay.
So I am trying to tell that this is the protocol these people provided, but I am telling that by doing some sigma x, sigma z measurement, and for the same measurement, they will check on some of them whether the results are correlated. If the results are correlated for the rest, they need not measure along x. They only measure along z and can get the key, because now they are sure that they are sharing a actual base state.
Exactly. Thanks. Okay.
So, but Gurudev,
Yes.
yeah, but in this case, the key rate will not be 1, no, because some of the run you have to use to certify the state is indeed 5 plus.
Yeah. But now, Manik, I am restricting myself that after being sure that you have a 5 plus, key rate is 1.
After that, the key rate is 1. That is true.
I am restricted to that. I am not calculating key rate for the whole thing.
I understand.
So let us restrict to the case that if you are assured the state that this is this, then the key rate is 1.
Oh,
now the question is whether this is the only state from which, I mean, whether you need 1 bit for getting 1 secret bit.
Understood.
Now we shall consider the scenario where eavesdropper himself is the supplier of the base state. So I am little bit trying to derive this thing so that my next discussion it will be good for the next discussion. And I have considered the most strong case, because eavesdropper is itself the supplier of the base state. So possibly this is the most favorable scenario for Eve to get the secret key. To be sure that supplier has really sent their state, Alice and Bob checks the following condition. When they select the same measurement basis, their results are correlated. For both the measurements, results are completely random. So secret key means also 0 and 1 will appear with equal probability. That has to be guaranteed also. Now to get the secret key, Eve as a supplier will try to correlate his system with the qubits of the Alice and Bob, because the supplier himself is eavesdropper, so he will try to correlate one of his system whose dimension may be more than qubit dimension to correlate with the 2 qubits that he is going to supply to Alice and Bob. So now the most general state that he can prepare with 2 qubits and his system is this. This is the most general pure state. No one should think about mixed state, because if it is mixed, then again we can purify it, and the system that is used for purification that is given to Eve, that can be given to Eve. That's why this is the most general shared state between Alice, Bob, and Eve. Condition to be obeyed by Eve as supplier. Now, problem is Eve wants to know the secret key, as well as he has to be proved that he is a honest supplier. But the results of spin measurement along z-axis has to be correlated. This restricts the choice, and the state has to be the following form. Now, of course, Alice and Bob will check whether results are correlated along z-axis, and to have correlation, perfect correlation along z-axis, the most general state has to be restricted to this point, because other 2 terms has to vanish. Both results are completely random. This has to be again guaranteed, which restrict the state further. So C00 and C11 both become 1 by root 2. So now the state reduces to 1 by root 2 0 0 5 0 0, 1 by root 2 1 1 5 1. But the results of spin measurement along x-axis has to be correlated also. So what we do, we write for qubit, we express this state in terms of plus and minus. Again, we get the 4 terms, but along the x-axis, results has to be correlated. So middle 2 term has to vanish. And you see, so the middle 2 term can vanish only when phi 0 0 and phi 1 are the same state, and that means phi 0 0 and phi 1 1 has to be the same state. Then the middle 2 term vanishes, and finally you get this thing. That means phi 0 0 for each system, phi 0 0 is equal to phi 1 1. So what you finally get, that is Alice Bob system is a base state, and each system is completely uncorrelated with the 2 qubits shared between Alice and Bob. Hence, eavesdropper, to be faithful supplier, has to remain completely uncorrelated with Alice and Bob. So this proof I told because it will help us to understand the next thing. Now we are trying to go to more general result. Now let us consider a state like this: row A, B, A1, B1, where A and A1 is in Alice's lab, and B1 is in Bob's lab, and the shared state is between these. This state is nothing but the previous one, actually 5 plus and tensor row A1, B1. Now, if you get the purification of this system, then see, it cannot correlate with 2 qubit Alice and Bob, because already we know that this is in a pure state, so nothing can be correlated with these 2 qubits A and B. So the purification will only be related to A1 and B1. But this is obvious because pi plus is a pure state. We want a state such that the measurement in the 0-1 basis on AB results in the following CQ state. So if Alice and Bob measure in the 0-1 basis, then they get this CCQ state. This CCQ state means you take trace for A1 and B1. So Alice Bob's qubit state is CC because measurement have been performed, tensor product rho E. Now you can tell that this state, so you can tell that if you take the original state and trace over E, this is a private state. But already you know it is trivial because already there is a 5+ state. So again it is like earlier one. Only the language I have used because I will be using this thing next. The important point that has to be noted that it only can correlate with A1 and B1 because I have taken it to be in general weak state. But that does not help it to get the secret key because 5+ remains intact, and after measurements actually the CCQ state is becomes like this. You can clearly see that if the state is completely uncorrelated with this classical state, and they will get the key. Now, I am telling that again, that already as I have told you, that if you want to get a private key, then if you consider 2-qubit system, the only solution is a Bell state. But now I am defining a most general private state. So obviously the system cannot be 2-qubit. It has to be more a multi-party system where more than one system should be in Alice's lab, more than one system has to be in Bob's lab. So I have taken them to be AA1, BB1. And the most general private state is of this form. So you see, I have taken these states, but I have chosen a U dagger, that means the unitary operator acting on this, where form of U is like this. It is something of controlled unitary operation, where controller bit is AV, controller qubit is AV, and unitary UIJ acting on A1, B1. So this is the most general private state, from where you can get a private key. Now, how to have it? Again, things are very simple. Now, if you start with a pure state which is correlated with it, so the most general correlated state is something like this. I think we agree. 0, 0, 0, 1, 1, 0, 0, 1. This is for AV. And psi 0, 0, psi 0, 1, psi 1, 0, psi 1, 1. It is for A1, B1, E. Again, this is the most general purification of this. If I consider a state like this, if I take the most general purification with it, then this is the most general state. Now, for required correlation, that means to get a key, at least in one direction, their results has to be correlated. And probability of those results, correlated result, has to be equal to 50%. So these 4 conditions has to be satisfied. So A010, A10 is equal to 0, and A00 mod square, A11 mod square has to be half. For 00 or 11 outcome for AB, the if state, let us look at the if state. So middle 2 terms should vanish. Let Alice and Bob measures along Z axis. Then the state collapses to 0, 0 or 1, 1 with equal probability at A00 mod square is equal to half and A1 mod square is equal to also half. Now, what is the if? What is the if state for 0, 0 result? So it is, you have to take trace over A1, B1 for the state psi 0, 0, which is the state for A, B, A1, B1 and D. Similarly, for the result 1, 1, let the if state is rho E1, and again you get it after tracing over A1, B1, and the state is psi 1, 1. Now, what is the secrecy condition? Secrecy condition means if state has to be same whether Alice and Bob gets up or down. So this condition has to be satisfied. Now, from Wolfman theorem, this psi 0, 0 and psi 1, 1, they are correlated. they are actually, they can be expressed in this form. You can take a fixed state, psi A1, B1, E, and from a unitary operation on one side, say S side, AB side, unitary operation on AB can give you psi 0, 0, and also unitary operator on unitary 1, 1 on A1, B1 can give you psi 1, 1. This point is clear? Because this psi 0, 0 and psi 1, 1, these are states of A1, B1, and E. Now I am putting a condition that rho E from both these states has to be equal for secret key. Then Boltzmann theorem tells that these two states can be generated from a single state psi A1, B1, E using two unitary operation on A1 and B1. That's all. I think up to this point, things are clear. Because if you take a fixed state and you can get thousands purification, those purification are correlated by unitary operator. Now if you want to write the state after all this thing, after all this, using all this thing, if you write the state of A, B, A1, B1, you get these four terms. And ignoring it, you get the private state, which has these four terms. I think up to this point, things are clear. And these actually can be written in this form.
But in, sir, am I audible?
Yes.
Yeah, so in this derivation, you don't take into account that the Alice and Bob's measurement in the x direction should also be correlated.
No. Here my problem is, at least I can get a direction along which things, results are correlated, results are random, and if system cannot know it.
I see.
The next question remains in BBM protocol. I have to be assured that I have been given 5+ state. Here I am not considering that. I am trying to find a state between Alice and Bob's lab such that it can give a private key. That's all.
Oh.
If I am assured that the state is this gamma A, B, A1, B1 has been given to me. That somehow I assure that I am not going to discuss.
Okay.
To assure that you have to make many measurements and have to be assured. Like in BBM protocol, you have to measure along both the axes. Then you can assure yourself that you are given best state. But I am not considering that question. I am considering whether I can have a state. I am trying to find the most general form of a state from where you can get a secret bit if you are guaranteed that that state has been supplied to you.
I see.
Get it?
Okay.
Now take a simple example. So this is a state where it is for AB it is 5+. With it there is another pure state between A1, B1, and 1 minus P, pi minus pi minus, and is for A1, B1 it is psi bar, where psi and psi bar are orthogonal. Now this state is actually of this form, where U is this, U is like this. But I have not written in this paper. You can check that this state is actually in that form that I have written. Now, if you have a purification with E, if you take a purification of this state with E, then the state will be like this, where E plus and E minus are to be orthogonal. There will be no other. I mean, whatever purification you take, the state by state of Eve here appearing here and the state of Eve appearing here have to be orthogonal. Otherwise, tracing over Eve will not produce this state. Now you can rewrite this state in this form. You can rewrite this state this form. Because I have taken 0, 0, 0, 0 will come from 5 plus as well as from 5 minus. So take 0, 0 together and then state of A1, B1 and eavesdropper will be this, and plus 1 by root 2. The state of AB is 1, 1, and this is the state of A1, B1 and D. Now, if Alice and Bob performs measurement in the sigma z basis, their result must be correlated. If it is 0, 0, then each state will be like this. Because how to get the each state? From these state, you have to trace over A1, B1. Then each state will be like this. When that as a result of Alice Bob is 1, 1, each state is again the same. Because then each state has to be calculated from these state by taking trace over A1 and B1. But it will give the same state. So each state remains same whether Alice Bob's results are 0, 0 or 1. So this is a nice example. Instead of taking this state of A1, B1 and here and A1, B1 here, I have taken pure state. If you take two mixed state but orthogonal, two mixed state, you can replace these two by two mixed state. But if you keep them orthogonal, then again the same thing can be derived that when Alice gets 0, 0 or Alice and Bob gets 1, 1, each state will remain same. But I have taken simplest example. But I'll be giving another example.
So, but
yes.
Yeah. So in the pure case, means where A1, B1 both are, in this case, psi and psi bar are pure. In that case, at least Alice Bob share one EBT entanglement.
But I am telling even if this state of row A1, B1 and here, if they are even mixed state but orthogonal.
Understand. Now I'm saying that I understand. There you want to go. I'm saying in pure case, at least entanglement is still, it is actually 5 plus. But mixed state, something interesting you are trying to say.
Yeah.
Because less entanglement actually.
Yeah.
You can go to, you can still ensure one private bit with less
Actually, Manik, you are
entanglement.
correct. Actually, what Eve can do, Eve actually can help them to get 5 plus 1 bit of entanglement.
Yes.
Because E plus, if E measures in the basis E plus and E minus,
Yes.
okay, then Alice and Bob with their qubit will get 5 plus, and if he collapses on E minus, Alice and Bob will get 5 minus.
Yes.
Ignoring the A1, B1 part. So 1 bit of entanglement, Eve can help them to get 1 bit of entanglement. Still, the form of the state is such that once Alice and Bob measures on these two qubits along Z-axis, his Eve state becomes same.
If state, that is understand. I'm saying that this state has one EBT entanglement that I can see from first line. No, first line also.
But anyway, this either A1, B1 or Eve has to help.
Exactly. No, I'm saying from first line, A1, B1 is kind of flag.
Right?
Yeah. A1, B1 is kind of flag, small in kind of.
Yeah. And two orthogonal state can always be distinguished by LOCC.
Yes.
That's why I'm telling that either A1, B1 or E can help them to get 1 bit of entanglement. So basically, it is a pseudo 1 bit kind of
entanglement.
But now I'll come to an interesting result.
I'm just asking this question. This psi and psi bar are orthogonal. These are necessary. The psi and psi bar are orthogonal.
Yes.
Actually, it is necessary. Otherwise, it will not come in that form that I discussed.
Or not only that, you see, each part will not be identical.
Yeah.
If you trace out.
Hey,
Okay.
Keep in your mind that all these states are in this form, where U is this.
Okay.
But you can break this thing and finally we'll see that the states are in this form. this form is a necessary sufficient form for 1 bit of secrecy.
Okay.
But
And
this is
that
a very
makes this
different example,
cyber
and Manik told that there is already a pseudo 1 bit of entanglement.
yeah. I mean, that's why I'm asking for this pseudo 1 bit of entanglement. If the psi and cyber are orthogonal, then obviously there is a 1 bit of entanglement. But if the psi and cyber are not orthogonal, then we cannot make sure.
Now, if psi and cyber are not orthogonal, then the state may not be of this form.
Yes,
Exactly.
I got
Your
it. Got it.
privacy condition will not be satisfied.
Good. Okay.
From now on, you keep in your mind that this is the necessary sufficient condition for having a 1 bit of secrecy. This is the most general state. All states should have this form. Maybe the state does not look in this form, but finally the state can be reduced in this form. This is a very interesting example. Here, what you do, like earlier case, P with 5 plus, this is symmetric state between A1, B1, and again 1 minus P, 5 minus, again symmetric state. Now, if as this A1 is in Alice's lab and B1 is in Bob's lab, okay, you don't think that though these two states are orthogonal, they can be distinguished easily. If A1, B1 are in the same lab, then these rho S and rho A can be distinguished. Because it is a mixed state, proper mixed state. But don't think that by LOCC, these rho S and rho A can be distinguished easily. Actually, distinguishing among them will be very difficult, or at least for large E. Now, from these states, these rho S and rho A, as they are orthogonal, again you can get 1 bit of secrecy from this state. Now, interestingly, if you calculate the log negativity of this state, this log negativity is this. And you know log negativity is the upper bound of distillable entanglement. And you see, if D is very large, then log negativity is almost 0, and you can tell that is distillable entanglement is 0. Here, this gamma means big gamma. This small gamma should be replaced by big gamma. I mean, for this state between Alice and Bob's lab, where AA1 is in Alice's lab, BB1 is Bob's lab. For this case, the entanglement of this state for large D is almost 0. I mean, distillable entanglement. But still you get 1 bit of secrecy.
Sir, this rho S and rho A, that
Yeah.
means they are basically PPT entangled states.
No, why? Why PPT entangled state?
Because you said that the distillable bound of okay, the distillable bound is so this log negativity gives the upper bound of the distillability, right? Now, actually, Alice and Bob, they can actually distinguish 5 plus and 5 minus. Okay, so
Yeah.
they can eventually create either rho S or rho A.
Yes.
So, but we know that for these full states, this tau AB, A1, B1, these full states is actually not distillable.
No. When you are considering distillable entanglement, it is very difficult to calculate distillable entanglement. But I am trying to tell that you take this whole state, calculate
Yes.
its log negativity, then
Yes.
for high D, for large D, its entanglement is almost 0, but still you keep in your mind there is a theorem which tells that if you can get 1 bit of secrecy from a state like this, then distillable entanglement is non-zero.
Okay.
In whichever way you construct such kind of a state, is distillable entanglement is non-zero. But here what I am trying to emphasize, that you get one bit of secrecy from this state. But
Okay.
still, this distillable entanglement is very low.
Very low. Okay. Okay. Got it. It is very low, you are saying.
Yeah.
Right.
That's why
It could
D
be
tends
positive,
to,
but
the
Yes.
limit of this D tends to infinity is almost zero, something like this. But there is a result that private estate cannot, the distillable entanglement of private estate is non-zero.
Okay. And just I want to just need one clarification about the NPT-ness of this rho A and rho A, rho S and rho A.
So rho S
Are they
and rho A.
NPT, rho A, are they NPT states or not?
I
Rho
This might
A
be like
will be
one-
NPT state, but rho S I am not sure.
Yeah, because the symmetric subspace, no, from one or that class, the boundary, if we look NPT
Yes.
boundary, the range is parameter
That is
range we
there.
can find.
I got it.
It is by Shai state, like convex mixture of Shai state.
5 plus, 5 plus.
Psi.
Yeah. Psi.
Same Shai. Shai for A, Shai for B.
Okay. Yes.
If
Okay.
you take collection of all Shai for every Shai, then that subspace is called symmetric subspace.
Yes.
And this orthogonal subspace will be antisymmetric.
Guruda, can I ask
Okay.
one question?
Yeah.
Yeah, as you said, this rho S and rho A under LOCC, it is in general very difficult to distinguish these two states.
If you can, then you get one bit of entanglement.
Exactly. In general, it is very difficult. But there I am asking the question. So let's say we choose another rho S and another rho A, for which the distinguishability probability turns out to be under LOCC turns out to be just guessing probability. Means data
Just-
hiding. Guessing probability, half. Data hiding state. That state on which one bit data will be hidden, that state we choose, let's say.
Yeah, actually, Manik, instead of rho S and rho A, we can use some nice hiding state provided by Warner.
Understood.
Then easily it can be understood that one bit of entanglement cannot be created.
Yes, but in that case, finding log negativity might be difficult. That depends on the structure of the state.
Yeah.
Because here the beauty is the EN has a very beautiful upper bound is there.
Yeah.
I can make this a guessing probability, but still it has some symmetry of that state. But whether log negativity is some beautiful analytical expression one can find there.
But that example provides nice answer to Mead's question.
Yes.
Because I will put a hiding state, some hiding state here, some hiding state here. Then there is a result that those two states cannot be distinguished by LOCC. It is equivalent to coin tossing. Yes.
But I have one question, Manikda.
Yeah.
So is it possible to have two states which are in finite dimensions, which are distinguishable, which are not distinguishable by LOCC with exactly guessing probability?
No, it is possible. No, that is the Winter's result. Of
It
course,
is not possible, right?
very high dimensional state.
Means in finite dimensions, it will never be half.
Or with large number of qubits, you can create such a state.
Yes.
Then it will be almost half.
Almost half, yes.
Yeah.
It is
But
acceptable
this
result.
is the example, no? This is the example which will be almost half for large
No.
D.
Is this the example or little bit twist you have to do? Because DiVincenzo, they have to do something, no, here. This is not exactly symmetric and asymmetric, these two states. Hiding state is little bit different.
Yeah, hiding state is different. Of course, Warner's hiding state may use this rho S and rho A. They take most possibly rho S plus rho A by 2. Now, copy, it's the n copies.
Exactly, something like that. So, a little bit to trick one has to do little bit.
Yeah.
Oh.
Ensure the hiding condition.
You can look at Warner's paper in PRL.
And
I see. Okay.
He has provided many hiding states. Dipinsenju actually first discovered this state with great effort. He took large number of qubits and provided two states that cannot be distinguished by LOC.
Yes.
Though they are
And,
orthogonal. Yeah.
and Dipinsenju's case, the motivation little bit get from distillation kind of things.
Yes.
Okay. Yes.
Yeah. Now my motivation is to show that there is PPT entangled state from which you can distill secret bit. Maybe the secret, of course, the rate of secrecy cannot be 1, because already I told if you take a private state, is distillable entanglement is non-zero.
Guruprasad, can I again stop you here? Means, since this is, I'm saying since lots of students are there, so in earlier slide, since your title, I'm saying, can you go back to the so since your title of these things is physics of secrecy, can you say a little bit more about that? Okay, this A1 B1 part is in some sense what it is doing. It is
No, nice question. It is
Yeah.
actually shielding.
yeah, exactly. If you just little
It
bit
is shielding in such a way that E cannot probe Alice Bob's results on qubit A and B. It is acting like a shield. I have a trivial example of shield first. Here I have given a trivial example of shield that E has to be correlated, then he cannot correlate with phi plus. He has to correlate with the shield part, A1, B1. But still it remains 1 bit of entanglement. Now I am trying to decrease the entanglement, but using the shield in a non-trivial way. Yeah, your nice question for the beginners. Yeah, so
That means
yeah, this A and B1, B1, they are acting as a shield.
Guruprasad, Aravinda has probably some question.
Yeah, the question is, without this shield, that means extra state, can't we get secrecy?
Can't we get?
Secret state?
Now, please repeat your question.
Okay, so you say that this A1, B1, this extra state is acting like a shield which provides the secrecy.
Yeah, yeah.
That clearly I understood. Suppose if I don't have this thing, okay.
If you don't have this thing, then EBT is the only solution that I told.
Okay.
Because I told that, so come to the...
That is the only solution. Okay.
For distilling a PB, is the maximally entanglement state necessary? Now, answer is for 2 qubit system, the answer is yes. But in general, the answer is no.
Okay. Now got it. Thanks.
So shield is required. Yeah, actually, this state can be written in this form. This is actually a state A, B, A1, B1, but I have written in AB basis. 00, 01, 10, 11. This is for AB. 00, 01, 10, 11. And the state can be written in this form. This is a state.
This is block diagonal form.
Yeah, this is a state. This state can be written in that form. There are 4 terms. You look at these 4 terms and then look at the matrix.
So, but clarification of clarity of this for the students. So this is not a 4x4 matrix. It is a huge matrix.
No, that is huge. This every entry is D cross D.
Exactly.
So this is again D cross D. This is not D cross D, even D square cross D square.
Yes.
So it is high dimensional matrix. These are high dimensional matrix. But for the convenience, I have written them. If you look at this thing, then you will understand. Yeah, look at this. This is a state. Then I am writing these 4 I am writing in the 0011011 basis, then it will take this form. And if you have forgotten to write,
Sir, just I have one
you
question.
take equal to this quantity.
Hello, Guru sir.
Yeah.
Yeah, I just have one question. So, the very first matrix, those in the matrix, that element should be row A1, B1, right? Or
Oh, yeah.
those are
Yeah,
A1, B1. That's why it's a very big matrix.
A1, B1. Because AB already I have used for the qubit.
Yes. Okay.
A1, B1. Yeah.
Okay.
Child, thank you.
Yeah.
All this AB will be A1, B1. Yeah. Now, if you this U00 row AB U11, it may not be a density matrix. It may or may not be a density matrix. I tell it operator X. And similarly, U11 row A1, B1, U00 dagger, I name it, this is nothing but X dagger. Then this diagonal element can be expressed in this way, and they are indeed density matrix. Because from this form also they are density matrix, and you will see that they are indeed density matrix. Because if you calculate XX bar, XS dagger, you will get this thing. So this is the density matrix square. So if you take the root, then you get this density matrix. So you will see why this form is good for the next discussion. So this is the form of the private state where AB are qubits and A1, B1 may be large dimensional system. Now we are going towards secrecy from bound entangled state. What we do, we take a density matrix and we take two private states, gamma 1 and gamma 2. But one of the gamma 2 is rotated by sigma x by applying unitary operator on A, qubit A. So here if it is phi plus, it is also phi plus, the AB state, then actually this becomes some psi plus. Because if gamma 1 contains phi plus for AB, then this state contains phi minus for AB. Because sigma x acting on qubit A. So I am actually destroying the correlation to some extent with probability 1 minus P. Now I am not going to purify all these states and it will be very big. But it is true that if we construct the purification of this state, measurement in the 0-1 basis on qubit A and B results in the following CCQ state, where you have ignored A1, B1. For A, B, E, CCQ state will be like this. See, again, here we cannot get a perfect key. And the results are to some extent correlated with Eve also.
So,
Get it?
Guru, the first line, gamma 1 and gamma 2 are
Huh?
different. Gamma 1 and gamma 2 are different. No, first line.
Gamma and gamma 2 different, but even you can take them same. But what you have used, whether gamma 1, gamma 2 are different, they are different for A1, B1. AB part you have kept them same, so that sigma x, after action of sigma x on A, phi plus becomes phi plus.
I'm saying, let's say gamma 1 and gamma 2 are identical.
And then still it will work.
No, but then why rho E and rho E perpendicular bar is coming?
Oh, because these two are orthogonal state.
I see. Yes.
It's your orthogonal state, that's why if state has to be orthogonal.
Understood.
But it's still, EB is somehow correlated now. You cannot tell that EB is completely uncorrelated.
Yeah.
And not only that, you cannot get perfect key also. So what you do, there is a Debatago inter protocol which tells that you can get the quantum mutual information between AB and AE, then the key rate is this. This we will discuss. We will be discussing in our in some next lectures. But for the time being, you accept that for this CCQ state, rate of key, secret key, is greater than equal to quantum mutual information between AB minus quantum mutual information between A and D. And if you calculate this quantity from this state, it is 1 minus HP. So till P is not equal to half, you get positive. There is a positive rate.
So this I of A colon AB, that is one that is easy to see, no? If we that is easy to see. If we just trace out rho E part,
you calculate quantum mutual information.
Understood.
Though it is classical correlation like thing for AB at least, but
Yes.
you can use the standard formula for quantum mutual information.
Understood.
SA plus SB minus SAB, SA minus SA plus AC minus SAE, like that.
Understood.
And you get this because you know that now there are anti-correlation also. That's why key rate cannot be 1.
Yes.
And it is 1 minus HP. So till P is greater than half, you get key. Now these state, if you write in this form, then earlier these 4 terms were not there. Now these 4 terms will come because now 0, 1, 1, 0, all these terms will appear, and the whole state, this state will be of this form. Now let me tell my aim, what I want to do with this state. I want to choose x1, x2 in such a way that I can assure 2 things, that this P, if you take partial transpose over this state on BB1 part, I mean, if you take partial transpose on BB1 part of this state, the state remains invariant, which will tell me that state is PPT. And next thing I have to show that P1 is greater than P2, P1 plus P2 is equal to 1. P1 is greater than P2, that will assure secrecy. So 2 things I will try to see. One is the state is PPT. How to show that? You have to choose x1, x2 in such a way that if you take partial transpose of this state over Bob's lab, the state remains same. That will guarantee the state is PPT. And second thing, P1 is greater than P2, so that you get a positive rate of P. That will prove that you have a PPT state from where you can get secrecy. This is the aim. Get my point?
Yes, yes.
Now things are a little bit technical. So I don't have much time, but I'll send you the slide and references also. So I choose a operator WU in this way. Here it is in D cross D system. This UIJ is a unitary operator acting on a D-dimensional system. Then if you calculate WU dagger WU, then finally you get this. And if you take WU dagger WU to the power half, because this is a spectral kind of thing, you get this thing, mod of this thing. This. And this is actually you can see this is not a state, but if you normalize it, it is actually a state, product state. Product state on A and B. Sorry, it should be written as Sahil corrected me. It is A1, B1 actually. Because AB I am using always for qubit, 2 qubits, and these are large dimensional systems. So this is actually a density matrix without being normalized. And also mod of this W, which is the trace norm, this is nothing but summation over ij mod of uij. And define another define x2. So here I define x1. Define x2, which is same, but only you take partial transpose over b1. Same W, but take for x2 you take partial transpose over b1. And again you calculate all this quantity. You can finally see, again, this is a state without being normalized. Again, product state. And mod of this thing.
X1 is the exactly product state. You are not
Yeah,
separable.
earlier one is also a product state.
That's why I'm saying product state, not separable.
Yeah.
Pure product state.
No, pure, separable.
Separable state, I see.
Separable state. I should not tell product state, separable state. Separable state, and not only that, separable in computational basis. Separable in computational basis also. Here, this you have started with x2, for which you have taken partial transpose of W with respect to B1, and if you calculate this quantity, again, this is also a separable state without being normalized. Because it is JJ for A tensor, JJ for B. So this is also a state without being normalized. So if you consider this state, so now you see that these four, Now, if you take partial transpose of this quantity with respect to BB1, first you take partial transpose with respect to B. So these two terms will interchange, and these two terms will interchange. Other things will remain same. So in the next slide, so only thing, this thing will go there and this thing will come here. This thing will go there and this thing will come here. So now you take partial transpose over B1 for every term. For every term, if you take partial transpose, then you can check that I told that all these are separable state. And not only separable state, it is separable state in computational basis. So if you take partial transpose over B1, it will remain same. And you will see that I have not written that matrix. This matrix will go in here and this matrix will come here. Similarly, this matrix will go there, this matrix will come here, and then you have to take partial transpose with respect to B1 for all the terms. Now, diagonal matrix will not be affected. Now, after taking partial transpose over B1 for P1 X1 is nothing but P2 X2. So P1 X1 with partial transpose of P1 X1 with respect to B1 is equal to P2 X2, and partial transpose over P2 X2 over B1 is equal to P1 X1. If you use this thing, then you see that after partial transposition with respect to BB1, the matrix will remain same. Because diagonal matrix will not change because it is separable in the computational basis. And this, after this exchange, when you take partial transpose, it again becomes this same, this one. Because P2 X2 will go to the corner, but if you take a partial transpose with respect to B1, it will become P1 X1. So partial transpose of diagonal elements will not change as they are separable in the computational basis. So the state remains invariant under partial transposition. So one condition we have made, that we have made the state PPTS. We have row A, B, A1, B1 to be a PPTS state. That we have assured. Next, we have to assure that at least some secret bits can come from this state. For the distillable key rate already we have seen for such a state is HP1, 1 minus HP1. Now we have to choose things so that P1 is distinctly greater than P2. Now take the ratio of P1, P2. So ratio of P1, P2, from the definition that I have used, so, sorry, I missed something. Oh, my P1 is WU mod test norm of WU, test norm of W plus test norm of WU with partial transpose with respect to B1. This is my P1. And my P2, I have forgotten to write. My P2 is mod of WU partial transpose over B1 and denominator is this thing. So after some simple calculation, actually you will get these two. So P1 and P2 have to be chosen properly in terms of test norm of WU and WU TB1. So that the state remains invariant under partial transposition. So what I have forgot to written exact form of P1 and P2, but I tell you P1 is this, P1 is this, and P2 is nothing but WU TB1 mod of this thing, but this denominator is this thing. So with this choice, actually you get these two relation and the state remains invariant under partial transposition. Now you have to assure that P1 is greater than P2. So already you see that test norm of WU is equal to summation over Ij, Uij, mod of Uij, and test norm of WTB1 is equal to D. So for any unitary, you have to choose the unitary in such a way that in the Ij basis, there is more than D non-zero entries for this unitary. If that is guaranteed, then P1 is greater than P2. And as the secret key rate is non-zero, the state must be entangled. So the state is PPT, positive key rate showing that a state is entangled, so it is PPT entanglement. So finally what you get from a PPT entanglement, you can get secret key. But for that, this U has to be chosen properly so that it has at least more than D non-zero entries.
So, Guruprasad,
So Hadamard kind of unitary operation will be very good for this thing, but not sigma x, sigma y, sigma z. But if you consider A1, B1 system also qubit system, then kind of unitary operator that you have to choose is Hadamard, not sigma x, sigma y, sigma z. Yeah.
yeah, I'm saying this HP1 at the first line, HP1.
Yeah.
So can I make choice of unitary such that this HP1 is tends to 0, or there will be a lower limit?
Oh, yeah. Now let me tell you this one. Tell me what is the highest value of this quantity? Someone?
D square.
D square or D? No, not D. Actually, yeah, you have to manipulate this one to increase.
Yeah, understand. Not D square. It's a ratio, no?
It's a ratio. If there are D square entries, then also.
Unitary, all are not one, something.
Yeah.
Yeah, but we can have an eigenvalue decomposition, right? And all the eigenvalue has mod 1, right? For the
Yes.
unitary.
Yeah.
So can we not say that what should be the maximum value of mod of Uij?
Yeah.
It is
Mod of
exactly the number
Uij
of time, right?
summation can be greater than D square, right?
Yes. Means if it is a D cross D unitary, then there will be, it can be maximum D, right?
No, no.
No, Shahil, then, no, Tamal, then P1 is equal to P2 at most. One you require.
But somehow, as I remember, this P1, P2 can be 1 by root D, something like that.
I see. Okay, that we can check.
Yeah,
No
I think mod of all these elements is maybe sum of SVD values, because this is one of the norm. If I
Yeah.
remember. See, this is one of the norm. Sum mod of all the elements of an operator is a norm. So that is equal to sum of the SVD values maybe. So that is how they are taking some. It is a norm. Whatever the upper one for the unitary operator, it is acting. The numerator.
So you are saying it is sum of the single.
Manik?
So is it in singular value?
Yeah. That is that.
Understood.
Yeah.
That okay. That you can check. No problem.
Yeah, it has been discussed somewhere,
Understood.
but I forgot. So let us come to my final slide. So this KD, there is some bounds on KD. So this is the relation. So KD is in between ED and DC. But there are examples such that KD is strictly between ED and DC. This KD is greater than ED. This is trivially true. But the good bound is KD is restricted by regularized relative entropy. These are some bounds. So you can check these references. This was the first one where Hirotaki derived secure key from bound entanglement, but that was not this kind of thing. That was like from every 2 qubit entanglement, you can, by recurrence protocol, you can get a one bit of entanglement. It was like that. They started from a PPT entangled state, and they showed that if they take infinite copies of such a state, they can get a private state. So the rate was 0. But what we discussed, that comes from the second paper. There we get a finite rate of key from PPT bound entangled state. And in this paper also, you will get that we are discussing, you will get this highest value of the ratio of P on P2. So I'll suggest you to see at least the second paper, IEEE Transaction on Information Theory, volume 54, number 6, 2008. This is a nice paper that you can see. I think I have finished. If there is some question that we will discuss.
So last paper is by Hirotaki, Oppenheim.
Yeah.
So Guruda, I have just one question.
Yeah.
So again, I'll go back to this title of the talk, physics. So you see, shielding part I beautifully understand. That is the beautiful physics. It is happening.
Yeah.
I'm saying now let's come back to the next part. This where PPT you are going.
Yeah.
Can you just hear? So you take somehow 2 mixture.
Yeah.
I'm saying, can I do instead of 2, 3 mixture or something kind of things? No, that is not possible.
Yeah, but you are starting with simple things.
Understand.
You are starting with simple things. You take just 2 terms and you make the next one so that it becomes, its correlation becomes weak. As a
No, I'm saying, if I take three term, you see,
Yeah.
two term has something beautiful things. You look into the row AB part of the first part, means row CCQ form.
Yeah.
This AB part on the first part with P fraction and 1 minus P fraction AB part, they are orthogonal completely.
Yeah.
But if I take 3 term in qubit, that I cannot manage. Something overlap will come.
Yeah, still according to DW protocol, you can get some key.
some key. I'm saying, will that, I'm trying to look into from physics perspective, can choosing that kind of state give me a little bit better key rate or something? That it is not immediate because it's boiled down to calculation.
Yeah, because you see, to create a PPT bound entangled state, you have to do a lot of things, lot of choice.
Exactly.
And actually, in the paper, they have given a 4-qubit example where A is a qubit, B is a qubit, A1 is a qubit, B1 is also a qubit, and this unitary operator they have taken to be Hadamard.
Understand.
This unitary operator they have considered to be Hadamard.
Okay, anybody has any questions, then you can unmute yourself and ask the question.
I have one question.
Yes.
Guru sir, so the gamma operator that you wrote, no, the most general form of a p-bit state.
Yeah.
So yeah, the gamma. Yes. So this gamma, can it happen? Can that happen, or is it shown that basically the
Sahil, your voice is breaking.
question?
Maybe I am not hearing properly.
Hello.
Please repeat.
Yeah, Sahil, repeat yourself. Your voice was breaking.
Yeah, can you hear me? Can you hear me now?
And now,
Yeah.
Yes. So I'm saying that is it possible to get one perfect bit from a PPT entangled state? Perfect private bit.
So because initially I told you, if a state give perfect secret bit, the state is necessarily distillable. The distillable entanglement can be very low, but distillable
I see.
entanglement is non-zero.
I see. Okay.
So there is no chance that you get one perfect secret bit from a PPT state.
Understood.
You don't try. And not only that, there is another result where it tells that if you take a private state, whatever the most general form of, if you take a state of this form, it violates Bell's inequality.
Oh, I see.
That has been shown by possibly Acid and some other people.
Okay.
So they are distillable. Their distillable may be very low, but the distillable entanglement is non-zero and they violate Bell's inequality.
Oh, CHS.
Hello. Maybe it is just a guess or just a kind of an intuitive thing that you see, for getting a perfect private bit, a perfect, you should have DC-level entanglement 1, right?
No.
Non-zero.
Huh?
Non-zero.
No, perfect.
Perfect.
This state gives perfect. This state gives perfect bit. Perfect secret bit.
Yes.
And in DC level entanglement is not 1. It is non-zero. If you restrict me to C2, then it is 1.
Yeah. That is. Sorry. Actually, I am restricted to C2. That's why. Yes. Sure. I am restricting to C2.
Yeah. Then you go ahead.
Then one perfect entanglement is required.
Yes.
Yeah.
So I am saying that this may be a consequence of the fact that in qubit you cannot have a quantum channel which has private capacity but not quantum capacity.
Yeah, they must be related. Yeah.
Right. Yeah. That's why.
They may be. Yeah. Or if you restrict to qubit, then for perfect secrecy, you need entanglement.
Yes.
And for perfect teleportation or other quantum task, you need perfect qubit.
Right. Yeah.
So, but Tamal, I'm trying to see on 2 qubit things are Are all states are one-way distillable?
2 cubic, no?
Okay. Now, can't I have an antidegradable state which don't have any key rate? Under
Antidegradable.
one-way distillable.
Yeah, antidegradable means one-way distillable, right? One-way non-distillable, right?
Yes.
But you have
No,
some private
antidegradable can't have a key rate, no?
can't have a key rate.
With forward communication, but with backward communication, it could
Yeah,
have.
you are saying about qubit, right?
Yes, cubic.
Yeah. Then it's true.
Manik, just a second, Manik. The antidegradable means there is a way for Eve to reproduce Bob state,
Yes.
Yes.
right? Then
Yes.
antidegradable will not have key rate, right?
No, I'm saying I'm taking now help of backward communication. So Alice is taking help from Bob's communication. Now you can have a key, no?
I see.
Yes.
Like the Bennett argument.
Yes,
like,
yes.
Understood.
But I see. I understand your Kamal intuition, but yeah, a little bit more rigorous things is required.
More, sorry. I couldn't-
More rigorous argument is required.
Yes. I understand. That's why I'm saying that maybe
Yeah.
an intuition.
Understand.
Yeah.
Yeah, any more question? Guruda, can I ask one more question?
Yeah.
Yeah, it is kind of little bit just mathematical curiosity. What is physical motivation? I don't know. So you see, let's say you start with the maximally entangled state. If we three parties share a GHZ state,
Yeah.
then these three parties can share a secure key.
Yeah, kind of. Yeah.
So in that direction, people have developed something, and then multipartite entanglement distillation, something. Yes, multipartite entanglement distillation is not a very good concept that I understand. But any research or study, that.
I have not seen, but of course, the similar kind of approach may be done. But their PPT question can be raised only in all the bipartite cards.
Bipartition card, because the multipartite distillation is not a very good notion. But still, whether something can be physically, operationally motivated, something can be defined or something can be studied.
Yeah.
But I'm thinking, okay, this is a very natural question. We have to think, because people should think in this direction, and maybe it is very not operationally motivated, something beautiful will not.
Yeah, and put the condition of PPT along all. If you take three party, put that PPT condition that in every bipartite card the state has to be PPT. Yeah, that will be a good approach.
No, I'm thinking even more. I'm thinking about this Bennett UPB C2 UPB complement state. This is even all cut separable, but I know something peculiarity is there.
Oh,
whether that has some implication in key, tripartite key or something.
Yeah.
Okay.
So yeah, actually you can use various states whose properties you know, you can get nice results. But here it is by construction.
Yeah.
It is by construction. So this is not the only possibility, no?
So okay, if there is no more question, we can stop here for today.
Yeah.
And thank you, Guruda, for nice talk, and we'll join again. Yeah.
From the next talks, I'll be discussing for the student. I think it will be for the newcomers, at least it will be very helpful that I start from Shannon's theorem itself.
Okay. So Mir, can you say anything?
Yeah. So next talk will be Wednesday. I think the Thursday is 1st May. So, but I'll give a reminder, obviously. And, yeah. So see you around the same time.
Thank you, Guruda.
Thank you, everyone.
Thank you, sir.
Okay.